So the first topic today is like fundamentals of electron diffraction and 4D STEM, right? So we have a very diverse set of attendees here. So what I want to cover first is the sort of introduction to the conversion beam electron diffraction. That's the main technique that we use for 4D STEM using under like scanning transmission electron microscopy mode. Later, I'm going to explain a little bit about the 4D STEM and show some of the applications of that throughout like examples from literature and also examples from us here at Northwestern. And the first and the last topic would be I will share some of the applications in soft hard interfaces and soft materials, which is like one of the driving forces for nuance and shine resources here. So to start, I really like to start my talk with this diffraction pattern here. This is one of the first, if not the first, conversion beam electron diffraction taken. That was back in 1938. And you might recognize some of the names like Kossel and Mollestadt. They did this, if I remember correctly, this is a mica sample, and it was done at 45 kilovolts. And then a lot of microscopes today, it still takes exactly the same thing, right? So a lot of things happened in the last 80 years, right? In terms of hardware, software, and also knowledge of like research knowledge about how that happened, basically. Just to summarize like a few modes, most of you are probably familiar with like a parallel diffraction. It's also called like select area diffraction, right? So the SAD for short. So that's the one that you're most familiar with. So you usually start, when you start learning TM, we start by taking diffraction patterns, checking like symmetries of materials and doing like nice diffraction modes, such as like diffractive image modes, such as bright field and dark field. But there are more that you can do if you actually converge the beam. And these are a few examples here. As you change the convergence angle given by this 2 alpha value here, you can achieve like a different conversion beams, basically, right? So from the left to the right here, you can move from a smaller convergence angle, which is like a Kossel-Mollestadt pattern, to a Kossel pattern. So you can use this variety of modes in the conversion beam to determine different properties of materials. Here, one fun fact that I learned like this week, this picture here in the middle was actually taken by Professor Reis that just talked early today. So few applications throughout the years that you can see for conversion beam electron diffraction. One kind of like easy and direct is the thickness determination, right? So as you move from like an edge sample, for example, you can go for this sort of a pattern here with some conversion beam electron diffraction pattern that has more features, and you can use those features to determine the thickness and then later other properties. Another application for conversion beam here using a much larger convergence angle, also called like large angle conversion beam electron diffraction, you can use to determine lattice strain, especially in the semiconductor industry. Researchers have used that a lot in the past years. So you can use the high order Laue zones interference here in the center pattern of the CBAD to determine that component. Also, local symmetry. This was very like widely applied, very wide application for conversion beam electron diffraction. So I can give you a few names here to search later in the literature, for example, groups in Japan, like Mishashi Tanaka, for example, here in the US, folks like John Steed, John Spency, and other folks that work with them, like Jiman Zhu here in Chicago too. You can use that to really localize the term, like very localized point group and local symmetry here. Another a little bit more advanced information that you can get from conversion being Electron diffraction is the following structure. Here you see a nice example. It's a comparison. It's a silicon sample that you can actually determine like the following structure using conversion beam Electron diffraction. Other more advanced application for CBAD is structure factor, and from that you can determine the charge density map. So this is a nice example too, one of like a very famous back in the late 90s, where like Jiman Zhu together with John Spence, they determined this charge density map of a cuprite sample using refining the structure factors using the CBAD here. A little bit more recent example here, folks from Monash in Australia, they use a condition that is more like close to the zone axis to similarly determine the charge density distribution in an aluminum sample here. So as you can see, there are a lot of information that you can extract from CBAD, and this is just, we just like scratched the surface there. So with that in mind, we can think about how to expand that, right? So most of, I guess all of the examples that I showed in the beginning were done in like sort of like conventional mode when you are in like a TM mode in your microscope and you converge the beam and take the diffraction, right? So now you can use with the evolution of hardware and in recent years, and later with the evolution of detectors, you can capture those simultaneously with the scanning transmission electron microscopy here. So this is an introduction to 4D STEM. So for those that are not familiar with STEM, so this basically have your lenses in your microscope, converge the beam to a point, and then you create, if you are in a vacuum, you create this scattered beam on your screen. When you insert the sample there, the sample scatters the electrons, and you can collect those the information, actually the image, using like annular dark field, for example, or bright field, right? But you miss a lot of information when you cover your actual CBAD, your conversion being Electron diffraction here. And then with the evolution of the detectors here and the more specific the direct detectors here, you can actually simultaneously acquire your annular dark field and a diffraction pattern. And then I'm going to show you later today during the live demo how can you play with that, and with help of Gatan, you can synchronize. One of the examples is like a K2, K3, and 1 cameras. You can synchronize that with your imaging acquisition, and then acquire a diffraction pattern or your conversion being Electron diffraction pattern at each probe position during acquisition of your annular dark field image. So, and this is an example here. This would be your final data, right? So if you scan your probe across your region of interest, you create this mesh or this matrix of conversion beam patterns that you could use to extract all the information that I showed in the beginning, right? You just have to learn how to extract that. And then for that, later, Anna and Stephanie show some examples using digital micrographs, GTN software, and also Python, which a more like flexible way to extract those information. So as you can imagine here, you can from each of these diffraction patterns carry a lot of information that can be retrieved. So as I mentioned before, over the past years, there is the very rapid evolution in terms of detection, and that really propelled the usage and the application of the 4D STEM here. So some of you might be familiar with this. This is how we used to collect images and diffraction patterns in the microscope using like film cameras. And then this is a nice chart put it together recently on a review here. Using film cameras, you basically collect 1 gigabyte per hour at the most. And then on top of that, you have to learn a new skill, how to develop those films, right? With the CCD, there was an increase already like 4 times of data collection, and then really exploded after the insertion of direct detector and high-speed cameras here. For example, today, the detectors that we have here at Northwestern can collect roughly like 4 terabytes an hour if you're constantly using it to collect either images or diffraction patterns. So as you can imagine, this becomes it is still a scientific problem, but it will becomes a data problem basically. And then you do need new data management strategies and this is something really to keep in mind when you are purchasing a new camera or trying to establish a technique such as 4D STEM here. And then for that, there are a lot of development in the community. I can give you some names later on the chat and some references to look at. So one thing that I can mention here is that there's this group of people at NIST here in the US working on trying to establish like protocols for data management. So this is something, again, to keep in mind when you start working with that. Now, a few examples for like 4-dimensional STEM, as I can show in the beginning, what you can get from this large data sets, right? So the first example, and then the most simple thing to do, in my opinion here, would be like a virtual imaging and a structure classification. So here is a nice example of a metal alloy, the references at the bottom. So you can, instead of doing your typical bright field, dark field imaging under TM mode, you can collect that set of data, the set of diffraction, and use those virtual detectors that to integrate different parts of your diffraction pattern and create those like bright field and dark field virtual images, like we call. So for example, B here is an image that was formed by integrating only this spot over here. So the left is corresponds to the red, and the D corresponds to the green spots here, which are like the dim ones. So this is already great, right? So you can do collect a bunch of data on that sample, lots of diffraction patterns, and then play with that the rest of your PhD, basically, right? With 4 terabytes of data. So other things that you can do, like structure classification, right? So you do can differentiate, for example, like amorphous from single crystal from polycrystalline. And then as you can imagine here, some of you are already thinking about throw some advanced algorithms here, such as some sort of artificial intelligence, machine learning algorithm to speed up the classification of such large data sets. Another example here, and this is a nice one that I really like to show here, is this three-dimensional classification of grains. So you can expand this to this 4D data and collecting like other like a tomographic data set, right? And then classify those different grains according to like tilt and so on. There are a lot of other examples here. These are the ones that are relatively new. There are other works that started before using CCD that was not like branded as 4D STEM. So you can search for scanning diffraction, nano being electron diffraction, and I guess nano being scanning diffraction too. So there are a bunch of nomenclature that people have used before for these STEM that basically do similar work using diffraction patterns and really like lay the foundation for analysis in 4D STEM here. So the other nice application here, which is like fairly easy to, is the orientation mapping, right? So here is a nice example for a battery material, lithium iron phosphide, that has a bunch of grains, and then using diffraction patterns, you can basically classify the orientation and so on. So another nice example that just came out was using 4D STEM approach under SEM, right, in transmission mode. So uses like low voltage and then still possible to classify like a large area and a bunch of different grains in graphene in this case here, just to show the large possibility of applications for orientation mapping here and different voltage ranges too. Another a little bit more advanced application, it is the strain mapping. This is also an example from 2015 using 4D STEM, covering a pretty large area of the sample. So if you compare this to a traditional like GPA analysis, like geometrical phase analysis, you gain a lot more information, and you don't need to necessarily have your disk completely aligned. So for example, regions like this, if you can see my mouse here too, is a little bit off axis, but as long as you can see the diffractions that you're interested to analyze the variation in reciprocal space, it's still possible to reconstruct the strain, to plot the strain tensors and plot the strain maps here. So another application here for strain mapping is this sort of like low tilt grain boundaries and driven by like dopants and similar like other like another atomic insertions or doping, for example. So so just to show the how robust is this technique to when you go across like defects, for example, right? So another application, local symmetry, and it's basically going back to that local symmetry using the traditional CBAS, right? So here you basically expand that to a larger area, right? And then you go, this is a silicon sample with a defect in the middle. So as you go across that defect, you see how that changes the matrix here that determines how far off of the symmetry is the diffraction pattern. Another example here on a ferroelectric material, you can measure that variation in polarization, right? And you can plot some sort of like a polar map or a map of your polarization based off your diffraction pattern. And here I was using two specific diffractions here, like a 020, which is the one that is sensitive to that polarization or the variation of polarity. Other more advanced applications that 4D STEM has enabled in the past few years is like phase contrast imaging, such as differential phase contrast. So here I have two diffraction patterns that are collected from two different materials. So here, the one at the top, I'll play it again, has a lower potential. The one at the bottom has a larger potential variation. So like electrical, the inner potential of the sample. So by capturing those diffractions and those the variation in the center disk, you can place those virtual detectors that I showed in the beginning, right, and plot images like this, and plot and combine that and retrieve the electric field vector and then electrostatic potential here. So, and that can be done like simultaneously to your ADF image. So you have your nice high resolution STEM image that you are familiar with, plus the information that you capture from the diffraction pattern. So another a little bit more advanced application here is a technique called typography. So typography it was more largely developed in the optics community, although it was initially the initial concept was for electrons, but it ended up being more applied to in the optical field, and then more recently in the X-ray community. So by capturing those diffraction patterns, you can also use those interference, the interference regions of your conversion beam disk to retrieve the basically the phase information of your object here, your sample, right? So and then I'll show one quick application that we're doing here at Northwestern later in the talk. I'm not going to go into too much detail on those two, but feel free to connect later in the talk or send an email. We can discuss further. Or also there are like a lot of references that we can post later too. So few applications here that I want to show in soft hard interfaces and soft materials using direct detectors. So one challenge of imaging this type of materials is, first of all, being sensitivity, right? Especially using STEM on using like standard alignments or standard emissions, current emissions that you use for your hard material, right? So you basically destroy your sample after a first pass on your typical HADAF or annular bright field imaging here. So some of you may be thinking now, so there are a lot of developments in cryo-EM, right? So that led to a Nobel Prize a few years ago. But how about you want to do something more localized, or even taking advantage of the multimodality of STEM, right? So collecting also not only your image, but your chemical information, perhaps your taking like spectroscopic images such as use of EDS, right? So it becomes a challenge, and first of them, as I mentioned, was the beam sensitive, and the second one is the poor contrast, right? Because most of the soft materials are made of like carbon, oxygen, hydrogen, and very low Z elements here. So this is a nice example that shows one of the strategies to to go around that using phase plates in TM. This is a TM image, right? So you see that without phase plate, you basically don't see too much from your biological sample here. So when you add that shift in phase using the phase plate here, you can enhance that contrast. This is something that can also be done in STEM and collect in a 4D STEM fashion. Again, just contact me. I can send you some references on that using phase STEM for that application. So how are you going to come across those two challenging points here, right? So first thing is take advantage of the direct detector cameras to control your dose. So this is a nice example nice videos done by Benjamin Miller from Gatan using our K3IS here at Northwestern. So you can really control the dose while you acquire your data. And then I'm going to show you later on the live demo as well. And really, this is a TM mode just for reference. And you can really follow the morphology here variation while you control the dose, right? So you can unlock different variations of a sample by using this feature here, right? So one thing, all right, so you can do that. You can control the dose, you can lower the dose and have a high signal to noise using those new cameras. But how about in terms of applications, right? So one nice application here, this is done by our TM manager here, Dr. Paul Smith. So he used that 4D STEM to combine all those things, right? Looking at soft materials, which is a human enamel here, using 4D STEM and reducing the dose using the direct detector. So this is an example of a diffraction pattern from the vacuum where you can see a very good signal to noise ratio where you can definitely use that to extract information from your sample. So this is from the same work with help from Stephanie here that shows that with that level of signal to noise, you can do a virtual imaging like I showed in the beginning, and it can even go further by calculating the strain map, like in plane and out of plane strains here from the diffraction patterns. Another nice example here that this is very recent. This is like fresh out of the oven, basically from like last week. This is one nice example from one of the students here, Kelly Parker, that she works on this nice mega molecules called tetracutanease. So they're very low molecular weight, actually, in comparison to other structures that we image using cryo-EM. And then she's been working on different strategies to enhance the contrast. So the first one that she applied was like variation of voltage, right? So applying like low voltage on a stain sample, which is a method, like a preparation method for biologic materials to basically enhance the contrast of those species. On the right side here, I show, like I mentioned, like a very fresh example from typography reconstruction using diffraction patterns like the one shown here, that you can really see that the same structure, right? At least the morphology of that, the kind of characteristic, like 4 lobes of the structure on a sample that was not stained. So meaning that was like basically a pure sample at room temperature. So it's really, this is really exciting, and it shows like a great potential using like 4D STEM and then typography here in this case for biological materials here. All right, so that went fast. Okay, so it's 9:46 now, Central Time. So I'm going to summarize here just to make my points on the 4D STEM, and then I would say like the 2.0 of scanning diffraction, or what I like to call the second wave of 4D STEM, can and will expand the application of traditional feedback. So there are more and more people involved that, and then we are creating like a larger community on that, and especially in like in data analysis, as you can see on the references here. So as I mentioned, like this increase in usage and applications of 4D STEM is definitely a consequence of the introduction of direct detectors here, such as like K3IS that you're going to use later today. One nice feature that I really like to show is that with 4D STEM, we can definitely expand the STEM multimodality. STEM itself is already a multimodal technique. You can collect EDS, you can collect EUs, you can collect cathode luminances and other with different detectors. But by collecting that those diffraction patterns, you can definitely create different visualizations and then unlock different information from your sample. And this is a nice example made by Dr. Akshay Murthy and then Stephanie that is on the call here, using this is a graphene with the gold nanoparticle, and then you can create like a different images basically using just using the diffraction pattern here. You can enhance the carbon contrast. You can enhance the higher Z material contrast. So basically, trying to overcome this this challenge of imaging interfaces, especially like soft to hard materials. One thing that I mentioned again, there's a need for developers in data management and especially training of the new workforce. So this is one of the objectives of this workshop. So I hope you all get excited about it. And then I always like refer to this paper. This is a nice introduction to the technique, and then has a bunch of references that you can follow as well. So you can go and check.